Hey everyone, welcome back to another video breakdown where we look at another automotive system in order to better understand and troubleshoot these systems. And obviously you can see in this setup we are definitely going to be looking at something electrical. I have my oscilloscope right here in the background, and up here we have this interesting setup. So this video we are going to be looking at some different wheel speed sensors as well as analyzing their signals with this oscilloscope so we can better understand and troubleshoot these systems whenever problems arise. So the first thing you want to ask yourself is, well, where are wheel speeds? How are those speed sensor signals going to be relevant to an automotive system? What are they actually using that for? Well, whenever you look at, well, apart from the obvious, the actual individual wheel speed, which again, you look at your speedometer, miles per hour, kilometers per hour, giving you an indication of vehicle speed, that's just a very, very small part of the overall equation for a lot of the things the control module is going to be looking at the wheel speed for. One of the things in particular that we're going to be talking about more in depth is your brake system. So right off the bat, your ABS system is very important with regards to monitoring each wheel speed because it needs to determine if a particular wheel is locking up, right? Now for your traction control system, same thing, it's going to be monitoring the wheel speeds, and if it determines a wheel is beginning to spin up faster than the others, well, we know that the control module will instruct the engine to limit power and torque to the wheels in an attempt to control that slip, but then it's also going to apply the brakes, going to pulse it on and off in an attempt to, again, restore traction to that slipping wheel, or to the wheel that's spinning up, right? And the way that works is, for instance, if we have a wheel on the right that's beginning to spin up, losing traction, it will pulse the brakes on that wheel and it will divert the power. And again, we're assuming this is a rear-wheel drive setup, or it can be four-wheel drive, all-wheel drive, doesn't matter, or front-wheel drive. But we'll just say in this example, this represents the rear wheels. This wheel can be on like a slippery asphalt surface, like ice or water, doesn't matter. This one begins spinning up. The control module will again instruct the engine basically limit power and torque. And then we'll also pulse that caliper without the driver actually depressing on the brake pedal, right? So that wheel, what that does, it transfers power from the propeller shaft over to this wheel on this side that actually has traction on the ground. And ultimately, again, that's going to get control of the vehicle. And then, of course, you have your stability control systems, and that has to do with like your understeer, oversteer, to where this is going to be another input that the control module is going to be looking at and to determine how to actually bring the vehicle under control or to help assist the driver with that. And in reality, it's also going to be looking at what the driver is actually doing via the steering angle sensor, where they're wanting to go, versus what the vehicle's actually doing, the yaw rate sensor, and then comparing all of that data coming back from all these various input sensors, the wheels included, to better control the vehicle. But in this case, we're just simply going to be looking at the different wheel speed sensor types. So I have these different setups right here. The first one we're going to look at to understand what's going on is going to be this wheel speed sensor setup, but then eventually we're going to bring this setup over and this setup over so we can compare the different speed sensor signals between what a good waveform looks like versus what a bad waveform looks like, and then we'll kind of analyze what we see on here. So the first one we are going to look at is a type of, so generally before we talk about this, speed sensors are generally going to be classified into two different types. You have what's known as a passive wheel speed sensor, which is going to be this setup. And we have what's known as an active wheel speed sensor, which is going to be this setup and this setup right here. And don't worry, I'll talk about these a little bit later, more in depth. So the main difference between a passive and active sensor is a passive sensor setup is going to be generating its own voltage. They're also referred to as variable reluctance sensors. They're known also as magnetic pulse generator type of sensors. And then they are also known as like inductive sensors as well. So variable reluctance, inductive, or magnetic pulse generators. They all mean the same thing. They're all generating their own voltage. So because of that, from the vehicle, there's no actual power supply required for this to be generating a voltage signal coming out of there. And that is because, again, if you remember in the, now granted this is for my students currently attending brakes class, but inside of here, we know that there's going to be a permanent magnet with a coil, and we know that we have this toothed reluctor wheel. Let's see if this thing can focus a little bit better. So see that toothed reluctor wheel, like so? So this little adapter in green, this represents our drive wheels. Anytime the drive wheels rotate, where it's this reluctor wheel, because it's mounted to that, and they're going to be pressed either to the, they're going to be incorporated as part of the hub and bearing assembly itself, or it can be like on the end of a CV axle or mounted on a solid axle shaft, depending on the setup. But regardless, you're going to have some sort of toothed reluctor wheel whenever you are dealing with a passive sensor setup like this. Now, whenever each one of these little teeth, you can see how they're kind of raised up, every time each one of those teeth interacts with the end of this wheel speed sensor tip right here. And actually, let me go ahead and grab, let's see if I have a little screwdriver right here. So within there, there's going to be a permanent magnet. Let's see if this thing can focus again. So here's our wheel speed sensor. This is going to be rigidly mounted to the vehicle. Again, there's our securing bolt. You can see this is a 2-wire setup. We will talk about that in a second as well. And on the end of here, we have an iron core that protrudes out, and there's going to be a permanent magnet within there. And just for case in point, you can see this is magnetic. I'm not holding it. It's holding this up, right? So you're going to have this magnetic field that's radiating outwards, and as each one of these teeth come in close proximity to the sensor's tip right there, which we know has a magnetic field being radiating from there, or that's radiating from the sensor end, as that tooth comes in close proximity, basically what's happening is the magnetic field kind of distorts, and it wants to kind of follow the teeth profile in there. Well, whenever you have a changing magnetic field, you have to think back to Electrical 101. Anytime you have a changing magnetic field in the presence of a conductor, and inside of here, the conductor is the many, many turns of wire to form the coil, you have this fluctuating magnetic field in there, and whenever that happens, the changing magnetic field, the wire is exposed to that, and that's going to generate a voltage coming off of here. Now you can see on here they have a red wire and a black wire. This is straight from a vehicle harness, and assuming right off the bat, if you were looking at this vehicle, you would assume like, oh, red's power, black is ground. That's not the case with the passive sensor. This is going to generate an analog signal, meaning, now not every analog signal is positive and negative, but in this case, it will generate a positive peak, go back down to 0, generate a negative peak, and then return to 0 to form a cycle. So in reality, we have an alternating current that's generated as a result of these teeth, each one of those teeth of the reluctor wheel interacting with the sensor tip right here, or the magnetic field of that, which in turn is going to generate a voltage coming off of here, and then the computer is going to analyze that analog voltage signal coming off these wires, and then it knows basically how fast this particular wheel is rotating, right? So enough chit chat. Let's go ahead and take a look at this. So what I'm going to do, and to prove a point, I'll show you what I mean by how it doesn't matter which end of this we hook up to. So I'll hook up to the quote-unquote positive end with my oscilloscope lead. Again, all this is going to show right here is this is displaying what voltage is doing over time. So this is like a multimeter, but with a much faster capture rate, and that way we can visually see what's happening with the actual signal, right? So I'm going to hook in one lead here, and then I'm going to hook one lead like so. And we're going to take a look at the resultant signal in here. So I'm going to go ahead and run this. And I have the trigger set up for a relatively low voltage. And let's just go ahead and give this a quick whirl and see what we can start to see on there. So I'm going to change the time base on here just so we can kind of zoom in a little bit more on there and get a better look at this. So let me go ahead and move this over, and you can clearly see. So by the way, I'm going to make sure my arm's not in the way. Okay, good. So right here, this is our 0-volt reference line, right? And you can clearly see that we get these oscillations right here. Let me go ahead and reset this one more time. There we go. So again, you can see whenever I spin this, I'll try to go relatively slow. You can see that we have this sort of oscillation pattern on here. And what this is showing you is that's going basically from 0, positive voltage, 0, negative voltage, positive voltage, negative voltage, positive voltage, negative voltage, right? So remember, an analog signal, that's just voltage that's gradually changing over time. Now in the case of, well, what does this actually mean? Well, let me change this again so we can kind of better make sense of what's going on. I'm going to zoom out, We're going to do that same thing again, and then I'll bring a drill over here to kind of give you a consistent RPM hopefully on here. Now I'm trying to be as consistent as possible, and I'll stop in just a second. So right here it just seems like a bunched up mess right here, but keep in mind that I have it set up to where basically the distance from here to here, it may be hard to see on the camera, but basically each one of those divisions represents 200 milliseconds or 0.2 seconds. So within 0.2 seconds, if we actually zoom in, you can see that there's these oscillations or cycles that are occurring per second on here, and it's just going from a positive voltage to a negative voltage, and then it basically just repeats. So the thing is, with analog type of sensors, I'm going to do a little demo real quick with the drill. And unfortunately with the drill we may see some noisy spikes occurring on here, but ignore that and look at the overall pattern whenever I do this. And actually I'm just going to go off of camera, hopefully to kind of reduce the noise that's being picked up. I'll start off slow, start increasing my speed. Did y'all see what happened there? So at slow speed, we can see that, well, right here, luckily it calculates it for us. So right now it has about, we'll call it about 50 hertz, meaning there's 50 of those cycles occurring per second. And if you look at the amplitude right here, or you know what, let me actually change this. Let's actually get a physical measurement on there. So what I did there is I just had an option on here to where I can measure the peak-to-peak voltage. And that'll tell us something about the amplitude. So same thing, I'm keeping it at a relatively consistent speed, and we have about a 45 hertz frequency, meaning there's 45 of those oscillations or cycles per second, right? And then we have a voltage peak-to-peak value of, we'll say, about 230 millivolts, or 0.23 volts. Now let's see what changes whenever I increase the speed. Our frequency goes to about 100 hertz, meaning that there's more of those oscillations occurring per second, and you can kind of see that because of the fact that, oh, my thing's moving around a little bit too much. It's kind of hard to do one hand, but basically there's more of the cycles or oscillations occurring per second, right? So that's why the gap actually starts shrinking on there. There's more of those occurring per second. And the actual amplitude on there, we have a voltage peak to peak of about, we'll say 0.7 or 750 millivolts. And you can physically see that too. It's generating a higher voltage. Now I'm going to rev this up even higher, and then we'll talk about what happens next. So basically what happened next is you saw that the actual waveforms, or the distance between the actual wavelength, you see that actually shrunk, and that's because there's more of those oscillations occurring per second, right? And the faster that, I'll go ahead and bring this back into frame. Basically, the faster that this rotates, and you can even see that on here, the faster I rotate this, you can see not only are there more oscillations occurring per second, and this isn't showing you across 1 second of time. If we actually wanted to see, it would be about this, to where we would see what happens every second, basically. So you can see just how many of those cycles are occurring per second, right? We're just zoomed in on a small frame of that. But let's go ahead and put this back. But basically you can see that, well, the faster your wheel rotates, you're going to have more of those oscillations or cycles per second, but then we notice that the amplitude also increases as well, or the voltage on there. And that's just because of the fact that the magnetic field is distorting quite a bit more. There's a lot more activity on there, and that in turn is going to generate more voltage coming off of there. And typically you will have, remember at slow speeds, well, I can do it right here, we have a peak-to-peak value of about 500 millivolts, or half a volt, meaning the distance from the top peak to the bottom peak, if we physically measure that, is about half a volt at like slower speeds. But then the faster you go, those can go up to several volts typically on there. But the point of that is whenever you analyze this signal, overall it should be relatively consistent in amplitude. Now the reason why, or I'll show you real quick. I'm going to zoom out. Now you may notice whenever I operate this at a high rate of speed, you'll see like the waveform itself kind of has these weird little oscillations in the amplitude. And let me show you real quick. So one more time, I'm just going to spin this real quick. So see it has this like weird pattern like that? That's because the center of this is not perfectly concentric. It's actually moving away slightly. So the further away it moves, we actually have a dip in the amplitude a little bit. So in reality, on the vehicle, it should be fairly consistent. This still isn't awful though. And again, we're ignoring all the little interference peaks right there. But actually that'll give you a little hint about what we're going to talk about a little bit later on. But the point of this to remember is the faster the wheel speeds rotate, or the faster the wheels rotate, the faster that this reluctor wheel is going to spin, the higher the amplitude, and the higher the frequency of this. And it should be, again, a fairly consistent pattern on there is what we're looking for. Now, the next thing we're going to look at, again, this is what's known as a passive sensor. On this, it's generating its own voltage. Oh, and I forgot. What I'm going to do, I said I was going to do this. I'm going to swap these leads around. Now I'm going to put the quote-unquote positive lead. It's not really referred to that as that, but I'll just swap the leads over and let's see if anything changes. And you can clearly see, well, it doesn't matter which side of the circuit we're actually probing on, and that's because of the fact that, well, we have an AC voltage that's being generated. Okay, so now we're going to change things up a little bit and look at this setup right here. So the big difference between this setup and the one we looked at earlier is this sensor setup. Remember, this is a passive sensor, meaning it's generating its own voltage on there. There's no power supply required in order for this to function. However, on this wheel speed sensor setup, this is an active sensor, meaning that it requires a power supply in order to function. And that is because there are integrated electronics within this actual sensor itself in order to actually process the data and send that back to the control module for ultimately figuring out the wheel speed. But you can see it still uses a rotating tone or reluctor wheel that comes in close proximity to a sensor. And I would pick this up and show it to you, but or you know what? Let me undo this. That's okay. That way y'all can get a better look at kind of what's going on here. So hopefully you can kind of see that there's our sensor up here. And it's kind of out of focus, but hopefully you can get the idea. That sensor is in close proximity with the teeth, and as the teeth rotate, it's going to distort a magnet a lot of times within here, at least for this setup. And remember, they can classify these as Hall effect or magnetoresistive type of sensors. They're both going to be measuring the magnetic field fluctuations in different ways, and ultimately it's going to take that input data, convert it to a type of signal, and then send it back to the control module for processing. So I'm going to go ahead and out of frame, well, I'm kind of in frame, you can see me a little bit. I'm going to hook up my power supply back to this. Now originally I was using my benchtop power supply, but Lord man, that thing had a lot of noise on there. It's a switching power supply. So I just have this hooked up to a 12-volt battery on there. And that way we can see the signal that's generated on here is going to be a lot cleaner. It had a lot of noise whenever it was hooked up to my power supply. You can kind of see it's in the far right corner back here, but it doesn't matter. Okay, so what I'm going to do now is we're going to go ahead and run the capture on this. And same thing, I'm going to rotate our drive wheel, and we're going to see the signal pop up on here. And you can see, well, granted, I purposely made it a little bit not clear. That's not really the best way of describing it. But you may be able to already kind of see it. There is a difference on here. Remember, here's a hint. This is our 0-volt reference. This is plotting what the voltage is doing over time. And even though we don't really see much detail, with the exception of this little blip right here, you can see that, well, do we have any negative voltage? No, all the voltage is at a higher potential relative to 0. So this is only going to be outputting a positive voltage. If we go ahead and zoom in, let's go ahead and change the time base and zoom in on that signal. Let's actually do it real time. Let's see what kind of signal is generated. Does that look like an analog signal to you? No. This is a digital pulse signal. You can see that on here we have a Do I not have min voltage? Let me go ahead and enable that real quick. So remember, what defines a digital signal is a voltage signal that basically is rapidly changing. It's going from one voltage point to another. It doesn't necessarily have to start at 0, and this clearly shows you that. A lot of people think that a digital pulse signal is going from like 0 to 5 volts, back down to 0 to 5, when in reality, well, a digital signal is just a voltage signal that changes rapidly. A sudden change, right? So you can see that right here, at this peak, or sorry, not the peak, at this minimum voltage right here, it's actually dropping to around 640 millivolts. So that's the baseline voltage for that. And then it's going up to about 1.5 volts. So it's sweeping basically from 0.6 volts to 1.5 volts. And if we zoom in even further, let me kind of show you that in more detail so you can see what I'm talking about. So you can see there's our low end right there, our low voltage value. Then immediately, no, not really immediately, but rapidly it changes from this voltage point, goes from that lower voltage to a higher voltage, and then back down over here. Now what's going on? Why is this a digital signal with the rotation of this wheel? Why is it generating this type of pulse signal? Again, it has to do with the electronics on here. In reality, you still have a type of magnetic field distortion on there, but you have electronics on here that's going to process a very, very small voltage. We're talking about millivolts on here, and it's going to amplify that voltage and convert it into a digital signal, which is going to be sent back to the control module for processing. So they're going to take that small voltage, amplify it, and send it back. It's just a different way they do it. The question is, well, why are they doing it this way? Why don't we just stick with the good old-fashioned passive sensor? Like, it's less complicated, you don't need electronics, and it's simpler, right? But here's the thing. Let's see if we can spot some differences. So I'm going to bring the drill over, and I'm going to very slowly start ramping the speed up, and we're going to see what changes about this signal, right? Same thing as the passive sensor. I'll start out slow, and then I'll gradually increase the RPM, and we'll see what changes. So again, this is just a visual exercise for y'all. Increasing speed. Increasing speed. And slowing down again. Interesting. So what are some similarities? We'll go over that first. Well, and again, we know that this isn't ever dipping down into the negative voltage. It's a digital signal, different signal. But let's look at similarities first. So we know with a passive sensor setup, this guy right here, where we had the reluctor wheel in there and we were spinning it up, whenever we increased the speed, we saw that the frequency increased as well. And that is also true for this. Remember, even though we are looking at a different type of waveform, if we look at the start, and it doesn't matter where you start and measure this, if we look at the definition of a cycle, it starts here, drops down, goes here, and then basically just repeats. That's considered, again, one cycle or oscillation per second. Well, we can clearly see on this one that as I sped it up, you saw that there were more cycles or oscillations happening per second, just like a passive sensor, right? And again, I'll show you that. Here's a very slow rotation. You can see there's not as many. I'll go really slow, actually. So you can see not very many cycles per second. And by the way, to give you an idea of what this is plotted over, each one of these divisions is 20 milliseconds. So I'll kind of spread this out a bit more so we can see that waveform. So now I'm going to, we'll do 50 milliseconds per division. And you can see I'm going kind of at a slow speed, and then if I pick up the speed, you can see how it kind of bunches up and squeezes together. That's just because there's more of those cycles happening per second, right? And if I really speed it up, it really bunches together, and we can't really see very much detail, which is why, again, you zoom in so you can kind of analyze and figure out what's going on. But the point is, we can see the cycles per second is going to increase, the frequency increases. However, what is not changing on here compared to a passive sensor setup? Do we see any change in the voltage regardless of speed? So look, I'm rotating fairly slow, like at a snail's pace at this point. My min voltage is still 640 millivolts. My max voltage is still 1.44 volts. Let me go ahead and speed that up a little bit and see if anything changes. Min voltage, still 640 millivolts. Max voltage, 1.44 volts. Okay, let me really try and speed this up. yeah, it stays the same. There's no change in voltage, so we get a much more stable and consistent output voltage from this setup. The benefit with that is the fact that control modules can actually determine, or not determine, that's a bad way of phrasing that, but control modules can actually see vehicles going at a snail's pace or traveling very, very slow. So that's the bad thing about passive sensors, is the fact that, remember, as the reluctor wheel speeds up, you see it goes from like a low voltage or amplitude, and then the voltage signal basically increases relative to wheel speed. So the faster the wheel speed goes, for a passive sensor, the voltages or amplitude will increase. So usually at like 5 miles an hour and below, it's not going to be terribly accurate, and that's because the voltage coming off of the sensor is really, really small. So the wheels have to kind of get up to speed to output a strong enough signal for the control module to actually see anything. So at slower vehicle speeds, this isn't going to be very beneficial, but if you want accuracy, you need this type of active sensor setup. And that's because, again, it does not matter how slow the wheels are actually spinning. As each tooth passes by, it's going to see just these small voltage changes, and we know it's going to alter that signal, boost it, amplify it, and output a digital type of signal to the control module. So the control module is always seeing this input signal come in, obviously varying frequency, but the voltages are going to be consistent on there. Whereas this one, not so much, right? So even though, yes, there is a bit more complexity involved with this, this is going to be a more accurate type of system. So what I'm going to do, so active sensor. We know that it needs a power supply in order to function because of the integrated electronics in there, right? So that requires power, a signal wire. This is going to be, again, the signal that I'm tapped into. That goes to the control module for processing. And then ground. So we have 1, 2, 3 connections, right? So it's like, okay, well, on this passive sensor right here, I'm going to unplug it. So I have my passive sensor. Granted, I didn't really need to unplug this. I just realized that, whatever, it's fine. So you unplug the connector, and a lot of times it's kind of covered up to where you can't really see the wires. So you can see on this one it's covered up. We can't really see how many wires are being fed into this. This is an active sensor, by the way. We'll look at that in a second. Here's our passive sensor setup. So if you look right there, there's our terminals. You can see it's a 2-terminal design, 2-terminal connector, 2 wires, right? And we know that, well, that's all it needs, right? It's just going to be using that as our feedback signal wires for the control module, analog signal. However, if we go back to, so again, the point I'm trying to make with this is an active sensor, if you're trying to figure out the differences, or if you're troubleshooting a vehicle and you don't know if you're dealing with the passive sensor type of system or an active sensors type of system, well, you may think, well, active sensor, oh, it's easy, power, signal, ground, 3-terminal connection, right? Simple. Well, on this one, I unplug this connector, so you can see kind of down, this one's kind of hard to see, but we can clearly see on the connector, this is a 2-terminal design. So what gives? There should be 3 connection points, right? Power, signal, ground, right? It's a little bit trickier than that. So, case in point, let me kind of show you. Let's just pretend this is an active sensor. See on the sensor itself how there is a, well, you know, if it would actually focus, that would be wonderful. There we go. See how there's this little metallic collar or ring that's inserted into the plastic? So whenever you bolt this down to the vehicle, that prevents the plastic from getting crushed on there, right? And it can serve a dual purpose. The integrated circuit on there can actually ground out through this pin. So it would have a power wire feeding in, it'd have a signal wire going back to the control module, and then it would just ground out through this ring. Or the ground would actually be located inside of the control module, so it would be power, signal, and then the rest of the circuit grounds outside the control module. So don't always assume that 2 terminals means it's a passive sensor and 3 terminals means it's an active. Now granted, if you go to an actual, if you unplug a sensor and you see it's a 3-terminal design, well then immediately you know it has to be an active sensor because, well, power, signal, ground. So the point is if you come across one that has 2 terminals, you cannot visually determine the difference between them unless you absolutely know for sure on there. But an easy way to determine that is use a back probe connector. If you have voltage being supplied to it, well then, yeah, you're dealing with an active sensor setup. Unless there's a problem with the power supply, so again, it just depends. But anyway, now that we're hopefully becoming a little bit more familiar with what an active speed sensor signal looks like in the setup, we're going to take a look at this one right here. This is another type of active speed sensor, and again, it's either classified as Hall effect or magnetoresistive. I'm not 100% sure on which this one is, but you can see that this setup is it's a little bit different. So you can see it still uses an active sensor that is going to be in close proximity to a type of tone or reluctor wheel that rotates with the wheel hub. So as the wheels rotate, this reluctor wheel rotates, and then we have a magnetic field interaction in the sensor, which it ultimately is going to convert into a digital signal, and that signal is going to be sent back to the module for processing. So same exact concept, however, this reluctor wheel looks a bit different from what we're used to, and you can see the sensor itself is a much thinner profile. The permanent magnet is actually not located in this type of sensor. It's still going to have the integrated electronics. It's still going to be measuring for variations in the magnetic field strength if it's a Hall effect sensor, or it's going to be indirectly measuring it by changing resistances, and that's a magnetoresistive sensor, but they're both going to be outputting a digital signal. The result is the same. But what's going on with this reluctor wheel right here? How come there are no teeth on there? And if I'm talking about magnets, well, where is the magnetic field on this? If it's not in the sensor, where is it? It's actually going to be in this reluctor wheel right here. We don't see any physical teeth on there because it doesn't actually need it. And this can be really hard to demonstrate because I think this is, yeah, the magnetic field on this is just a bit too weak. But basically the closer I get to this, it's pulling the screwdriver down, and yeah, it's kind of a crappy demo. Let me do something that's a bit more convincing, right? Instead of saying, take my word for it, this is magnetic. You want proof, right? So here I have a magnetic field viewer, and what I'm going to do is I'm going to hold this over the top of the reluctor wheel, and let's see if we can see anything unusual. And in fact, we can see something interesting going on. And hopefully y'all can see that. Let me go to a new section on this field viewer. I'm going to try not to move it and smear it around too much, but see those segments? Each one of those line segments represents poles, meaning that could be a north pole, south, north, north, south, north, south, alternating poles all the way around this reluctor wheel. And those create sort of these little magnetic loops that come up and interact between the poles, to where as this reluctor wheel rotates, those magnetic loops interact with the sensor itself, the electronics process the magnetic field interaction, and send out an amplified digital signal to the control module for processing. So another type of active sensor that works basically, it's going to use the same concept and principle, but the way it's set up is going to be slightly different. So what I'm going to do now is I'm going to hook this up to our oscilloscope. Sketchy setup is complete. Let's go ahead and run this. And I'm going to bring this a bit closer so we can see what's going on, hopefully. And I'm just going to go ahead and rotate that reluctor wheel. And we can see we have a nice digital output. Now you may be going, wait, aha, I caught you. We have a positive and negative voltage is dipping below that 0-volt reference line. It's going to be an analog voltage signal. Even if that were true, if this were going to a negative voltage and positive voltage, well, it's still considered a digital signal because it's, well, I mean, it's rapidly changing. But that's not the point. This is our 0-volt reference down here. I just simply moved the scale, wrong dial. I moved the scale down so we can actually get a better view of this. So that's something you can do with any oscilloscope, is move our 0-volt reference around. But we still, the point is we still have a nice clean output digital signal that is going to, again, you can see the voltage on this one. The max voltage on here has changed slightly from the previous setup. On this one we're getting a max voltage of 1.58 and a min voltage of 640 millivolts on there. But actually kind of similar to that other one, just some very slight voltages. It's still not going all the way down to 0 and then up to a certain voltage. It just depends. Some manufacturers, they can have it sweep between like 0 and 5 volts, maybe go at a slightly higher peak voltage up here and a slightly higher minimum voltage. It just depends on what they engineered. So, but it's all going to be similar. So again, still the same concept. The faster the wheel speeds rotate, you get basically you have an increase in the overall frequency on there, and you see again the result of those cycles. They kind of, the waveforms kind of bunch up, right? And that's because there's more of those oscillations happening per second. However, something interesting happens whenever you use a design like this and you go backwards. Let's see what happens on this. Whoa, what the heck happened with that? We're getting all these weird spikes up here. So let's actually, and again, let's turn it this way. You can see we have this type of digital output. And then I go in reverse, and we have this sort of interesting looking output. So let's zoom in on one of those peaks and see, is that noise? Well, no, it's actually another type of pulse. So let's bring this, let's scroll this over so we can get a better look at this. Oh, it's just out of frame. But yeah, basically each end of those is pulsing up. It's, instead of going from 640 millivolts to around 1.5 volts and then just staying there, it actually peaks up to around 2.64 volts, drops back down, and is at a slightly higher voltage here, peaks up again, then drops back down. So the question is, why are they doing that? Well, that's so the control module can determine when the vehicle is actually going in reverse relative to the actual speed signals itself. And it's like, well, can it just use reverse as an input for that? Well, it can, but what if there's a problem to where it's like, just because the vehicle is shifted into reverse doesn't necessarily mean it actually is going in reverse. So this is yet another way the control module can determine which direction the vehicle is actually traveling in. So I think the best way to kind of explain what's going on with this, why we see these sort of voltage changes, or why we see this modified digital signal, is the fact that whenever the wheel, or reluctor wheel on here, rotates a certain way, the magnetic field, the way they have those poles aligned on here, it's going to interact with the internal circuitry on here differently compared to if it's rotating in the opposite direction. And the internal circuitry is going to recognize that magnetic field change on here, and it recognizes that basically, well, the vehicle's traveling in reverse. And the engineers, well, whenever it's traveling a certain direction, they want it to output a digital signal like this compared to if it's rotating in this direction. And there's not actually a computer in here, it's just the way the internal circuitry is designed and laid out inside of here, to where it's just going to create this type of digital signal in one direction, whereas whenever it experiences a different type of magnetic field interaction with that reluctor wheel rotating in that direction, well, then it outputs a different digital signal. So that's sort of my explanation without getting too into it. Last thing we're going to look at is how we troubleshoot some waveforms that aren't exactly appearing like they should. And we are back to our passive speed sensor setup. So just for reference, this is about, again, what a normal waveform should look like. Now what I'm going to do is I'm going to put this just out of frame, and I'm going to change something about this, and we're going to see what happens with this particular setup. Again, don't worry about that, I just picked up noise, so we're going to clear that. I'm going to just basically give it a spin and see if we can pick up any sort of weird things in the signal. I don't know if you're catching that, but something seems kind of odd on this. And let me kind of widen the time base on there so we can get a better overall view of this. Something seems very wrong at some particular points on here. Do y'all see what I'm talking about? Right there. Let's go ahead and zoom in and see what's going on with this. So, zoomed in, we can see again these nice oscillations. Again, it's going from a positive to a negative voltage. Nice smooth changes. It's all looking fine. And then you get this sort of weird, sort of like flat spot almost. Now it goes to a slightly lower negative voltage, slightly higher positive voltage. But the point is, we should see another pulse right there. It almost seems like it's missing, right? So what's going on with this? So let's try and spin it at a faster speed and see if we can detect that. Let me change the time base over a wider layout, and then I'll zoom in on one of those spikes. So let's bring this over here. This will make it more obvious. The faster the wheels spin, or our hub in this instance, the reluctor wheel, I'm spinning it off a frame just so you can't see what I did. And look at that right there. That should be more clear on this. So again, these nice oscillations, everything looks nice and pretty there, consistent. And then we just sort of have a large negative spike and a large positive spike. So we would expect to see, basically, it should continue that pattern, but there's really nothing there. Sort of a gap with a large, basically a large negative spike and a large positive spike. So what's going on with this signal? So the offender in this case, is going to be something's going on with this reluctor wheel. And again, we know we should see a consistent oscillation or cycle that continue through there, but in reality we see nothing. There is an empty space where there should be another pulse there. And if I bring this up close, I'll wait for this to focus before I start rotating this around. So again, looks good, and oh dear. We have a tooth that is missing. Now obviously I ground this down, but this could represent a broken or chipped off tooth on the reluctor wheel. And that makes sense, right? Because as each tooth passes in close proximity to the sensor, it is going to generate, basically, if we start from, let's zoom in on a nice looking one. So we'll say the start point's right here. So basically, as the tooth approaches it, we get a high positive voltage. Then whenever the top of the tooth lines up with it, there's no real magnetic field distortion, so it starts falling back down to zero. Then as the tooth passes the sensor tip, you have a tooth profile change, the magnetic field distorts, it kind of wants to follow that, so we have a negative voltage, and then whenever it lines up with the gap, then it starts kind of trailing off again, going back down to zero, and then the next tooth comes up to it, next tooth, etc., 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 right? But with our offender right here, again, at this point we should start to see it come back up, have another pulse there, come back down, and then just continue that. But there's nothing. There's a gap here. So yeah, we just sort of have, now I'm not going to go into detail why they have a negative and positive spike, but basically you can see there's a cycle there's basically a profile that's missing right here, and that could be, and usually that's going to be indicative of the fact that you have a chipped tooth. Now what if there were two teeth that were missing on here? Well, you would see two gaps on there, right? So from here to here, that represents one full wheel rotation to where the reluctor wheel spins once, right? And that lines up perfectly. Well, if there was a broken tooth here in 180 degrees, you would see two of those little gaps per revolution of this. So you'd see like a gap here, so there'd be double as many of those gaps on there. Well, what if the tooth was like broken here? Well, you'd see the gap shift over on this spot. There'd be a spot missing to where there's supposed to be an oscillation or cycle, right? And that makes sense because there's no interaction of the magnetic field, so you see that little gap in the signal. Now you may be wondering, well, what does that look like on an active sensor? We'll look at that in just a second, but it's easier to kind of understand this with a passive sensor, I think. So we'll clear this. We will increase the horizontal band, and let's give this a spin, and let's see what's going on with this. And again, this is purposely off frame so you can't see what's going on. Something looks horribly wrong with this signal. Good Lord, look at that thing. Again, the waveforms themselves look good, but then we have this weird little amplitude shift. See how it went from a large amplitude and it shrunk down to a small amplitude? Again, the voltages are what we're looking at. Then as it continues to rotate, basically it's oscillating. The voltages is going from a high voltage to a low voltage. Fairly consistently too. So again, I will spin that up, and yeah, it's not looking too great. What the heck's going on with this thing? So I'll give you a minute. You can pause and think about any theories you have for what's causing this. And I'll give you a hint. It has to do with the reluctor wheel and speed sensor interaction. Okay, now I'm going to bring this in frame, and I'm going to spin it again and see if you see anything weird with this setup. Does this look like it's spinning very true? Let me show you now from this profile. So look at that. See how it's wobbling like that? So what's happening is, and I'll bring this close so you can kind of see it. Well, basically what happens is around here, there's a pretty good sensor to tooth interaction, but then whenever it comes over to this side, basically it starts falling out, not falling out, basically it starts moving away from the sensor tip and not interacting as much. So the result is, the resultant magnetic field becomes, it's not distorted as much, so there's a weaker interaction between that and the sensor coil, which in turn is going to generate a lower voltage during that point in time. So you get these parts of the wheel where it generates, where there's good tooth interaction between that and the sensor, but then as it starts moving away from there, there's not as much interaction, you see the voltages shrink down. Now you may be wondering, well, it's like, well, when am I going to see that? Well, that represents an issue if you have some weird like ABS intermittent operation to where like the pedal's pulsing randomly, or you're getting like these weird speed sensor dropouts on your actual speedometer gauge. Well, that could be something like your hub bearing is starting to go out, and the resultant wheel is going to have a lot more excessive play, right? And that can cause, well, since this is going to rotate with the wheel hub assembly, if there's a lot of excessive movement on there, it can actually have that effect to where it's moving into the sensor path and out of the sensor path, and it will give something like this, right? See, and this can also be from incorrect installation of the speed sensor on like a solid axle assembly. Now we're going to take a quick look at what can happen. We're going to use the same setup to where we have a missing tooth and then a wobbly effect like this, and we're going to look at what happens on an active sensor setup. We're back with our active speed sensor setup. We have our reluctor wheel with the simulated broken tooth on there, and we are going to use our noisy ass drill, and I'm going to run this hopefully at a consistent speed, and we're going to see what the resultant speed signal looks like coming off of this sensor, and then we'll talk about the results in a second. Hopefully we'll stop this. Okay, good. Okay, so what you notice with this setup is we have, if we zoom in on the signal, we can see we have a nice consistent, or relatively consistent because the drill is kind of like speeding up and slowing down, but overall consistent amplitude looks good. The frequency looks pretty consistent as well. However, if you noticed throughout its rotation, there'd be small little gaps, or here, let me zoom in on this a bit more. Hopefully y'all are able to see that. So you can see right about here, wherever we expect to see another pulse, there's going to be basically a dead spot on there. And that simulates, again, every time that tooth, or the part of the reluctor wheel with the missing tooth rotates past that sensor, there's no change in the magnetic field, so it doesn't register that, so the resultant dead spot right here is, well, it's flat on there. And that will, ultimately, this will trigger it will log a trouble code in your ABS module, and it will also probably give you, well, you'll have your ABS warning light will illuminate, and then if your vehicle has stability control, traction control, a lot of times those warning lights will illuminate as well. And yeah, if you were to pull up the signal or the waveform coming off of there, and you'd see like these dead spots on there, a lot of times that's just attributed to issues with the reluctor wheel, there being like a tooth missing on there. I'm not going to go over every single waveform on here, but I'm just giving you some examples of what you can see out there, what's pretty common. What I'm going to do now is I'm going to pop in the reluctor wheel that simulates either an incorrectly installed speed sensor reluctor wheel, like on an actual solid axle, or a hub bearing assembly that's starting to get excessive slack and free play to where the wheel's basically doing this. So same thing, I'm going to, let me go ahead and zoom back out on this. We'll do 200 milliseconds per division, and same thing, I'm going to operate it with the drill, and we'll see what happens. So yeah, it looks pretty awful, right? So again, let's think about what's happening here and why we see this. So we know that as the reluctor wheel rotates, it's rotating into the, here, let me unhook this. So you can see basically right here, whenever the teeth of the reluctor wheel are interacting with that sensor, well, then you get the resultant pulses back there. But then, as it rotates around, it simulates, again, a wonky bearing that's getting too much slop or free play, it's starting to fail. Well, then you can see that it rotates out of the sensor path, and the resultant, you get these little dead spots or flat spots in the signal. So, some signals, nothing. Signal, nothing. So the signal's dropping out coming off of there. And then also, what's really important too, and this is true for both active sensors and passive sensors, is that actual sensor to reluctor wheel, the gap on there. You want to ensure that that clearance is set properly, because, well, you can have something like maybe the O-ring, you pull a sensor off for You know, you need to pull up a hub assembly, replace the bearing, and then whenever you go back in with the sensor, if it's not fully seated on there, like the O-ring on there is kind of dry rotted and brittle, you just hit it with your electric impact real quick and you hear it clack and you just turn away without actually tightening it down. Well, the sensor may not be sitting down flush all the way, and then the increased clearance on there with an active sensor, you'll basically get a dead spot, and it's not going to be close enough to even register the wheel speed on there. So you'll have basically a wheel that's not being picked up. The speed sensor signal is not even being generated on there, just because of the interaction between there. It's not close enough. Whereas on a passive sensor setup, if the gap is too wide, it'll be a very, very weak signal that'll be generated, and the control module, basically, it won't really see a wheel speed until, well, until the vehicle's traveling at a decent amount of speed before it actually generates an accurate signal, if that makes sense. So now, if we focus on this in the background, you can see there are the resultant dead spots. So that's where it's picking it up, and then basically nothing happens. And this is just sort of like it picks up on it briefly. Probably picked up on a tooth right there, and then yeah, you can see basically from here to here, it's not really picking up on anything. Then all of a sudden it's like, oh, I know the speed, no I don't. I know the speed, no I don't. And it's doing that consistently with the wheel rotation. So anytime you see a consistent pattern like this, a lot of times you want to be inspecting and figure out what's going on with the interaction between the reluctor wheel and the sensor. Again, consistency is everything. If you have this random erratic pattern going on, well, you may want to look elsewhere. There's something else that could be interfering with it. When in doubt, if you have these weird ABS or stability control problems, see if there's anything aftermarket installed on these vehicles. See some weird issues to where like aftermarket headlights can affect the speed sensor signal feeding back to the control module. So yeah, as usual, I try to keep my videos relatively short, but there's so much to talk about. So again, yet another long video that's probably going to be 40 minutes after I edit, but hopefully y'all learned something. And yeah, until the next video, bye everyone.